Welcome back. This is the second of the short videos about some of the fundamental mathematical concepts underpinning this module. This time we're going to look at averages. Okay, there are quite a lot of different types of averages. These are a few that you may have come across before. The mode, the median, and the mean. Now, I've illustrated these by using an example of a random variable, something that has different values at different times. And in this case, I've taken 5 samples of this random variable a at different times. I got 1 twice, I got 2 once, 3 and 13 once as well. I've plotted them on a histogram here. Histogram is just a plot of the value of a against the number of times that it occurred. Now, the 3 different types of average are calculated in different ways. The mode is the most likely value. In other words, the value that happens the most often. In this particular case, the value 1 happens twice as often as any other value, so the mode is 1. Now, if you didn't know anything about the possible values of a, and somebody told you that the average value was 1, you might be surprised to find that the value was 13 occasionally. 1/5 of the time, in this particular case, the value was 13. For distributions like this, the mode is not a particularly helpful definition of average. A slightly more helpful definition is the median. The median value is the value such that the probability of a being lower than the median is the same as the probability of a being above the median. So in this particular case, the value of the median is 2, because 2 out of 5 times a is below 2, and 2 out of 5 times a is above 2. They are equal, so the median is 2. Once again, for a distribution like this, just the median is a little misleading because it doesn't give you any idea that there might be a value out there at 13 happening. The mean value is the most common form of average, and it's worked out with this formula here. What that says is, you take the sum over all possible values of a of the value of a times the probability of a taking that value. So in this case here, we've got the value of 1 times the probability that the value is 1, and that is 2/5. I could write it out like this. The mean is the sum of the probability of a having a value times that value. So, the first value a can have is 1. The probability that a has a value of 1 is 2/5, because it has that value for 2 out of 5 times. The next value a can have is 2, and it has that value 1/5 of the time. It also has the value of 3 1/5 of the time, and the value of 13 1/5 of the time. And if you work all that out, the answer is 4. So the mean value of this distribution is 4, which is a little bit more reasonable. It's closer to what we might imagine the average value of all of these readings actually is. And when I say average, if I don't specify which type of average I'm talking about, I will mean the mean. That said, there is another type of average which I'll probably use even more often than the mean. And that other form of average is most useful when I'm trying to work out energies and powers in a circuit. When we start looking at electronic circuits, we'll derive equations that look like this. The power is the square of the current times the resistance. The resistance is usually constant, but the current often isn't. So if I want to know what the average power is, what I really want to know is what is the average value of the square of the current. There's a very similar formula. The power is the square of the voltage divided by the resistance. Again, the resistance tends to be constant in a circuit, but the voltage isn't. So if I want to know the average power, I want to know the average value of this. Because the resistance is constant, I can write that as 1 over R times the average value of the square of the voltage. Now, if I want the average value of the square of the voltage, that's not the mean voltage, or the median voltage, or the mode of the voltage. That's something new. That's the mean value of the square of the voltage, often called the mean squared voltage. And I can work out the mean squared voltage, but the problem with mean squared voltage is its units would be volts squared. Similar thing here. If I worked out the mean squared current, I could express that, but I'd have to give it the units of amps squared. It's not a current. And it's nice to have a way of expressing the average value of a current in amps and the average value of a voltage in volts. Now, if I work out the mean square voltage, that's expressed in voltage squared. If I took the square root of the mean square of the voltage, that would be a quantity that I could measure in volts. And that is the average, which is often the most useful when dealing with currents and voltages in circuits. It's the square root of the mean of the square of the voltage. That's a bit of a mouthful, so we usually shorten that. It's the root of the mean of the square of the voltage, the root of the mean of the square of the voltage, otherwise known as the RMS. Oh, I should just check that people are familiar with this terminology. Drawing a line over something like that means take the mean value. That is the mean value of the power. That is the mean value of the square of the voltage divided by the resistance. Anyway, back to this. This is the RMS average, the root of the mean of the square of the voltage. And it's probably the most useful type of average that we'll be dealing with in this module. I can do an example of working out what the RMS average is using the same distribution that we were looking at earlier. Now, the mean value of something is defined as the sum over all possible values of the value itself times the probability of the value. That would be the mean value of x. What we want for the RMS is the square root of the mean value of x squared. So if this is the mean value of x, then the mean value of x squared would be given just by doing that. And the RMS value is the square root of the mean value of the square of x. So let's work that out. It's the square root of, okay, well, x can be 1. 1 squared is 1, and the probability of x being 1 is 2/5. Next, x can be 2. 2 squared is 4, and the probability of x being 2 is 1/5. It's 2 for 1/5 of the time. X can be 3, which would make x squared 9, and again it's 9 for 1/5 of the time. And x can be 13, and 13 squared is 169, and again that is true 1/5 of the time. The 1/5 is the probability that x has that value of 13. It's p of x. Work all that out, and the answer you get, 6.07, which is significantly above the mean value of this distribution, which was 4. Right, that's all I want to say to introduce the RMS average. In the next of these videos, we'll be doing some examples of working out the RMS average for some common waveform types.